Hello students, welcome to the course Circuit Theory and Network. Today we are going to discuss about Thevenin's theorem. Generally, in our course there will be several theorems like Thevenin's theorem, Norton's theorem, superposition theorem, and we can solve any circuit by using that theorem. But each and every circuit must have to fulfill some criteria, and if the circuit fulfills that criteria, we can solve that circuit by using that theorem. So today, as we are discussing the Thevenin's theorem, so first of all we have to know that where we can apply this Thevenin's theorem. We can apply this Thevenin's theorem for any active network. Obviously active bilateral network will be there, and we can solve that circuit by using this Thevenin's theorem. And obviously if the circuit consists DC sources as well as if the circuit consists AC sources, no problem at all, we can solve the circuit. Just there will be little changes are there. Just changes is as we have seen in our previous cases, it means when we consider the DC circuit, we consider the resistance, and similarly if we consider the AC circuit, we have to consider for impedance. Just this little bit changes are there, and whatever the remaining concept that are the same. So before going to the Thevenin's theorem, first of all we have to know a particular network. The network obviously active network, active and bilateral network, and we can solve this network by its equivalent voltage source in series with a resistance. And this is nothing but the approach of the Thevenin's theorem. It means suppose a complicated circuit is given to you, as you can see in your circuit. It's a complicated circuit, the several resistance there. As an example, we have considered there are two different resistance and one resistance. This is suppose the internal resistance of this source is E, and there is only one sources is given, that is obviously DC sources. So for that particular circuit, you can represent this circuit in a simpler way, just like a voltage source and with in series with a resistance. Obviously this voltage source's value that is written over here as a VTH, this source does not have the same value with this E. It may be the same value or it may not be, that depends upon the calculation. So first of all, how we can calculate and what is this terms actually whenever we are going to convert a normal circuit into Thevenin's equivalent circuit, or we are going to solve the Thevenin's theorem, obviously two important things are there. One is called the Thevenin resistance and another one is called the Thevenin voltage. That VTH, it means that equivalent voltage over there, this is called the Thevenin voltage, and sometimes this Thevenin voltage, that is called the open circuit voltage also. And why it's called open circuit, that I am coming later. And that is RTH, this RTH, that is called the Thevenin equivalent resistance. So this is the overall structure. The same circuit, it's a complicated circuit. This circuit can be represented into this simpler type of circuit by using that Thevenin's theorem. Okay, now we are going to the next circuit, where we will see that what are the different steps is to solve this Thevenin's theorem. Okay. So for the Thevenin's theorem, obviously the circuit will have a sources. It may be AC sources, it may be DC sources, but for the simplicity of understanding, first of all we are going for the DC source and then we will shift to the AC network. Okay. So first of all, the circuit having several numbers of resistance, and there may be the several numbers of sources, and obviously there will be one resistance, and among there you have to find out that voltage or the current through that resistance, and this is the one thing by which you can solve, that is the Thevenin's theorem. So what are the steps? So the first steps is the remove the load resistance. So the first question may comes, what is load resistance? Load resistance is nothing but the resistance for which you have to find out the voltage across the voltage, or through which we are going to find out the current. It means in your question they are asking to find out, suppose the current through this 15 ohm, they are asking you to find out the current through this 15 ohm resistance, and that's why this 15 ohm resistance you have to consider as a load resistance. right? So first of all, you have to identify the load resistance. If in your question it's given to you that this is your load resistance, any resistance can be act as a load resistance, no problem at all. So if the load resistance is given to you, then no problem at all. If it's not given and in another way they are approaching to you that you have to find out the current through this R2 resistance, suppose so this R2 resistance you have to consider as a load resistance. Suppose if they ask you to find out the current through this R1 resistance, or they are asking you to find out the voltage across this R1 resistance, so first of all you have to consider this R1 resistance as a load resistance. So for simplicity, we have considered over here that as a R3 resistance as a load resistance. So the first step of this Thevenin's theorem, first step is the remove the load resistance from the circuit. So whatever the load resistance will be there, you have to remove that load resistance. And so whenever you are removing the load resistance, so if we remove this load resistance from the circuit, obviously here will be open part, here will be open part, and then you have to find out the voltage to that open circuit point or to that open terminal. It means in that open terminal, whatever voltage we are getting, that voltage is called the Thevenin voltage. That's why this Thevenin voltage is sometimes called as a open circuit voltage also. So what is the open circuit voltage? It means from where the load resistance was there, we have removed that load resistance, and in that place we are going to find out the voltage, and that voltage is called the open circuit voltage or Thevenin voltage, VTH. So this is our step number 2. Now we are shifting for next step. So next step is the remove each sources of EMF and replace them with their internal resistance. So next step is that you have to find out the internal resistance, because of we have seen that in case of Thevenin's theorem, there are in your Thevenin circuit there will be two main things. One is called the Thevenin resistance, another one is called the Thevenin voltage. So now next work will be to find out the Thevenin resistance, and to find out the Thevenin resistance you have to replace all the sources whatever present over there in your circuit. You have to replace all the circuit, and directly you cannot replace all the sources. If you want to replace any sources, you have to replace these sources by its internal equivalent resistance. Remember it very carefully. You have to replace all the sources by its internal equivalent resistance. Now the question may comes, what is the internal equivalent resistance for different types of sources? Your circuit may have some voltage sources, your circuit may have some current sources, obviously. So if there are any voltage sources are there, we know the internal resistance of a voltage source, that is negligible. So if there are any voltage source, the internal resistance as a 0, so negligible or 0, so we can replace the voltage source and we can short the terminal, right? Similarly, if there are any current source present over there, then we know the internal resistance of a current source is infinite. That's why whenever we are going to replace any current source, then we will replace the current source and we will keep the terminal open, right? So this is for the independent sources, if independent voltage source and our independent current sources are there. But if there are dependent type of sources are there, and already we know what are the dependent sources, there may be the voltage dependent voltage sources, there may be current dependent voltage sources, there may be voltage dependent current sources. There are different types of voltage sources or current sources, and different types of dependency may be there. So if these types of sources are there, then simply you have to find out this RTH by VOC by ISC. It means there is a different process. So first we will see how we can solve a simple circuit where only independent sources are there, then we will go for if there are any dependent sources are there. So first we have considered a circuit where only independent types of sources are there. So already we have find out the VTH, and then as we have removed all the sources in our previous sources, it means whatever the sources are there in our previous circuit, this is our previous circuit, already we have removed this source, this resistance, load resistance, and we have find out the voltage in this terminal. And in the same circuit we have to replace the source. If we want to replace the source, which types of source is this one? This one is a voltage source. As it's a voltage source, so what is the internal resistance? Internal resistance is negligible or 0. So you can replace this source and you can short the terminal. So what will be your next circuit? So obviously your next circuit will be like this. So if we are removing this voltage source, the terminal will be shorted, and then you have to look from the load side. It means as your load was here actually in this A and B terminal where you have removed the load, and you have to look from that load side to find out the Thevenin resistance or the equivalent resistance of the circuit. So look from this side, what will be your equivalent resistance, that you have to find out. And simply, you know, if we look from this side, from this load side, obviously we will see that this R internal, it means this 2 ohm resistance and this 8 ohm resistance, they are parallel to each other and then in series with this 4 ohm resistance. So that will be your RTH. So this is your step number 4, that we are finding this RTH. And the next is, whenever we have already find out this VTH and RTH, it means in our hand there are Thevenin voltage and there are Thevenin resistance. Obviously we can connect this Thevenin voltage and this Thevenin resistance in series with each other and again in series with the load. So it means at first we have a complicated circuit like this one, where the internal resistance was there and another 3 resistances was there, 1, 2, 3, 4, total 4 resistances are there, 1 different sources are there. So there are several series and parallel branches are there. It's a complicated circuit, and by using the Thevenin's theorem we are reaching in a simpler circuit, and that circuit have only the Thevenin voltage, have only the Thevenin resistance and have only the load resistance, and all they are in all are series. So now as they all are in series, so simply if we want to write that what will be this load current, and obviously we can find out that load current, that this load current is nothing but we can find out that this I is equals to, we can write whatever the voltage are there, or simply the voltage is VTH divided by RTH plus RL, RTH plus RL. It means whatever the resistance overall path, R load, here it's written as a R load, so that's why I am written as a R load. So simply how we are getting this equation, some of you have the confusion that we are getting, how actually we are getting this equation. Nothing, just simple KVL application, whatever we have seen in our last lectures, that apply for any closed path, we can apply the KVL, like whatever the current, just we have to know the current for this path. As here is the I current, obviously this capital I amount of current, it's flowing through this path. So simply we can, if we start from any resistance, so we can simply write that I into RTH, it means capital R of TH, capital RTH, I into RTH, that is the voltage across this RTH resistance, then plus the voltage across this load resistance, that will be nothing but a I multiplied with R into load, that is load, written like this, R load. And then if we, as we are moving in this direction, clockwise direction, and we are reaching to this voltage, that is VTH, so in negative direction, so that's why we can write minus of VTH, minus of VTH, that's what is equal minus of VTH, and there is nothing new and every element has been completed. We have considered all the elements, so we can write over here is equals to 0. So simply from this equation we can write VTH is equals to I into RTH plus I into R load, or if we take a common as a I, so we can write I is equal I into RTH plus R load is equals to VTH, and if we find out the I, then simply we can find that capital I in this equation that we are getting, actually this capital I is equals to VTH divided by RTH plus R load, that we can write. Okay, fine. So now next we have seen that what are the steps, are there. Now we will see that if practical problems are there, so how we can solve this problem. So till now we have seen the steps. So what is the steps 1? Steps 1 is you have to remove the load resistance, step 1. Step 2, in that where we have removed the load resistance, in that open circuit point you have to find out that voltage is called the VTH, and then after finding this VTH we are going to replace all the sources by their internal equivalent resistance. This is your step 3. And step 4, you have to look from the load side to find out RTH or the Thevenin resistance. And next you have to design a circuit, or you have to draw a circuit in series with VTH and RTH and in series with RL, and then put the formula and you will get the result. So now let's have an example. Okay. So now here some activities are given to you, that there are two circuits are given. Already we have seen these types of circuit, how we can solve it, and there is another circuit. You can try to solve it yourself, and I am going to another example to solve it. Okay. Suppose the second circuit was there, or this circuit. Suppose there is a circuit, there is a resistance, and two different sources are there. Here for the first time we have taken both the voltage sources, and one resistance are actually there, and we have removed that resistance in A and B. And if we go for the previous circuit, no, the circuit is not given. So for this particular circuit, here is one resistance, and you are asked to find out the current through that load resistance. So here the question is written over here, that obtain the Thevenin equivalent circuit for the network and determine the value of the load resistor required for a circuit for a current of 0.5 ampere for between the terminals A and B. So the same question is given to in another way. Sometimes they can give you that load resistance value, and they can ask you that what will be the values of the current, or what will be the voltage of the resistance. But here they are asking you in different manners. Different manners means a circuit is given to you, they are asking what will be that load resistance value if we want to pass a current of 0.5 ampere, right? So generally the question comes that what is the current if there are some X amount of resistance. It means the resistances are given and you are asked to find out that current. But here a trick is given to you. The trick is that they are asking you to find out the values of the resistance if that particular amount of current is flowing through that circuit. So don't worry, this is the same thing is given in another way. Okay, so where we have to find out the values of the resistance or the values of the current that has to be considered as a load resistance. So that's why this A and B terminal, whatever the resistance we have to connect it, we may consider that resistance as a load resistance. No problem at all. So as per our step 1, we have to remove that load resistance, and as per step 2, we have to find out the voltage across that open circuit terminal. Okay, so we have removed that load resistance and the circuit looks like this. Okay, and then you have to find out the voltage across this A and B terminal. So you have to find out the voltage A and B, and over here these 5 voltage sources and E2 2 voltage sources are connected over here, and simply you can solve this circuit by considering here by applying nodal analysis also. That will be very easy. Simply here will be two different nodes will be there. Here will be one node and here will be one another node or connecting points will be there. If we consider, then if we consider this one as a 0 voltage and this one as a voltage V, and by considering the currents, you can simply find out the voltage of this particular point and you can simply get the VTH. But here I am going to discuss another approach, one different approach, and that approach is how we can find out that voltage. So now as two different types of sources are given over here, obviously we can say that if plus 5 volt sources are given and plus 2 volt sources are given, and if we consider that this B point have a ground potential, so obviously we can say the voltage across this this point and with this point, that will be, this is plus 5 and this is obviously plus 2, and they are connected in opposite direction. So obviously we can say that voltage across this R1 and R2 resistance, that is 5 minus 2, that is equals to 3 volt. So it means the voltage across this R1 and R2 resistance, this is nothing but your 3 volt, but we have to find out the voltage across this AB terminal. So what is the voltage across this R2 resistance. So we know the voltage dividing rules. So voltage, as per voltage dividing rules, the voltage across this resistance R1 and R2, it means this point and this point. It means now the voltage of this point and the voltage of this point we are getting, that is equals to our this 3 volt. So what will be this voltage across this resistance? This is nothing but this 3 volt multiplying with the resistance from where we are going to find out the voltage divided by the overall resistance where the actual voltage is. So we can say the voltage across this R2 resistance, this is nothing but what is the overall voltage across these two resistance? This is nothing but your 3 volt. So 3 multiplying with, in which resistance we are going to find out the voltage? This R2 resistance. So 3 multiplying with this R2 divided by the overall voltage, overall resistance, that is nothing but 4 plus 6, that is nothing but R1 plus R2. So 4 plus 6, this is nothing but 1.8 volt. Similarly, what will be the voltage across this resistance R1? Simply we can say our total voltage is 3 volt, our total voltage is 3 into values of the resistance R1. So 3 R1 value is the 4, 3 into 4 divided by the overall resistance, that is means 4 plus 6. So we can say the result will be 4, that is 4 plus 6 is equals to 10, so that is 0.4. Obviously it will be 0.4, 3 into 0.4, that will be nothing but 1.2. So again we can find out this voltage 1.2, and here is given that 3 minus 1.8, it means this overall voltage is voltage across this R1 and R2 is 3 volt, and if we can find out voltage in this terminal, in this A point and this point is 1.8 volt, so what the voltage obviously this R1 resistance or across this R1 resistance, that will be obviously 3 minus 1.8, 1.2 volt. So you can go for this logic or you can go for this. Okay, so now already we have find out the voltage across this 4 ohm resistance and the voltage across this 6 ohm resistance. Now as we have to find out the voltage across this A and B point. So this point voltage obviously it will be your Thevenin voltage or the open circuit voltage VTH. So if we can write over here that this voltage is our VTH or the open circuit voltage, so simply we can write over here that this voltage is our VTH. So if we consider a closed path over here, if we consider, so we can say this voltage plus this voltage plus this voltage will be equal to 0 for this closed path. So we can write 1.2 volt plus VTH as we are moving for the positive terminal for this plus VTH. So 1.2 plus VTH and minus 5 will be obviously is equals to 0, and from here we can find out the values of this VTH. That will be, this will be plus 5 will be in right hand side and 1.2 that will be subtracted. So 5 minus 1.2 that will be 3.8. And similarly if we look for this circuit it will be also the same. Here we can write 1.8 as we are moving from the positive side. So here is the positive side, so the voltage is 1.8, then plus 2, 1.8 plus 2 minus VTH will be equals to 0 if we consider for this loop, and there also we can find out the same value of this VTH or as a Thevenin voltage, that is 3.8 voltage, right? Now after finding this Thevenin voltage, as we have already find out this Thevenin voltage, next our next aim will be to find out the Thevenin resistance. So what are the steps to find out the Thevenin resistance? So to find out the Thevenin resistance we have to replace the sources. Now which types of sources are here? Here are simply voltage sources, independent voltage sources, and we know the internal resistance of a voltage source, that is negligible or 0. So just replace the source and sort it, and again replace the source and sort it. Now your circuit looks like this. So here will be one resistance and another resistance, that is for your 6 ohm resistance. This path will be sorted, this will be normal, and here also your voltage source, that will be sorted. And as this is your 4 ohm resistance and this is your 6 ohm resistance, 4 ohm and this is your 6 ohm resistance, and we are going to find out the resistance in this terminal because we have to look from the load side. So where this is your load actually, so we are looking from over here. So if we look from over here to find out the RTH, so obviously we will see that this 4 ohm resistance and 6 ohm resistance, they are in parallel to each other. And if we know, if the resistances are parallel to each other, the equivalent resistance is nothing but a multiplied with 4 and 6 and divided by 4 plus 6, or simply we can find out the values of this RTH. It means as they are parallel, this 4 and 6 ohm is parallel, we can find out 1 by RTH. The actual formula is 1 by RTH is equals to 1 by 4 plus of 1 by 6, and if you solve it, that will be 24 divided, and in numerator will be 6 plus 4, and if we exchange it, the value comes that RTH is equals to 4 into 6 divided by 4 plus 6, and we are getting the ultimate value, that is RTH of 2.4 ohm. So whatever we are getting, that our this value is, that is VTH 3.8 volt, and we are getting RTH is 2.4 volt, right? And as we are getting this VTH and RTH, now what is our question? Our question is that for which values of the resistance we are going to send a current amount of 0.5 ampere or like this, that was there. One sec. So we are getting, actually this was our circuit, so actual current will be 0.5 ampere. So we have to find out this resistance value, this load resistance value, right? So now I am going to erase that part, erase that written over here. Okay. Now our next part is nothing. Okay. So this is our circuit, this is our RTH and VTH, and if we design the circuit as per our previous one, it means VTH in series with RTH. So it means here is VTH, and that value already we have find out, that is 3.8 volt, and we know the RTH having a value of 2.4 ohm, and in series with a load resistance that we know. We can consider one load resistance in the terminal of A and B, obviously over here, and if we consider that this is our R load, if we consider that this is our R load, so obviously this R load we can consider VTH, RTH and RL will be in series, and as per the rules of this Thevenin's theorem, we can write that IL, we know that what is our IL, we know the values of IL is equals to VTH divided by RTH plus RL, RTH plus RL, and in our question it's given that a particular amount of current we have to flow it. So what is that current? So if we go in the previous, that current amount is 0.5 ampere, load resistor required for a current of 0.5 ampere. So now if we go forward, so we can find that this current is, amount of IL is 0.5 ampere. So we can write in place of IL, that is our 0.5 ampere, and we know the values of VTH, and we have find out the values of VTH, that is 3.8 volt. We have already find out the values of RTH, that is our 2.4 volt, and we don't know the values of RL. So we have to find the values of RL. No problem at all. So simply from this equation we can find out the values of RL, and if we find these values of RL, and it comes like 5.2 ohm. So we have to connect this 5.2 ohm in that circuit in the terminal A and B, and so that we can get a current of 5.2 ampere. So that's, and in the next day we will go for the Thevenin's theorem for AC network. So what are the changes are there? So that's all for the day. Thank you.